All right, let's dive right into this. Welcome everyone, and especially to you undergraduate engineering students, to this explainer designed specifically for your communication engineering course. Today, we're going to completely demystify the core concepts of network models. Because let's be honest, if you've ever stopped to wonder exactly how a quick text message goes from the app on your phone, flies through the air, gets routed across the globe, and lands perfectly on your friend's device, well, you are in exactly the right place. We're going to take this highly complex architecture of modern data communications and break it down into clear, digestible, and most importantly, highly logical steps. It's like a giant puzzle, and today we're putting the pieces together.
Here is our roadmap for today's explainer. We're going to cover 1. The protocol layering concept, 2. The TCP/IP protocol suite, 3. Network devices and duties, 4. Encapsulation and decapsulation, 5. Network addressing basics, and finally, 6. We'll compare the OSI model to TCP/IP. Let's get to it.
Starting right off with Section 1, the protocol layering concept. To really grasp protocol layering, we need to anchor the theory in a real-world scenario. As engineers, you already know that we solve massive, complex problems by breaking them down into smaller, solvable pieces, right? Well, imagine two friends, Maria and Anne, just standing there talking face-to-face. We call this a single-layer protocol. Everything is happening all at once in one unified space. The primary interface for their exchange is simply to listen and talk. The set of rules they're following, the protocol itself, is just their shared language. It includes basic social rules too, like greeting each other or taking turns speaking so they aren't just shouting over one another. And the physical medium carrying the signal? That's just the air between them. It's incredibly simple. And because they're right next to each other, a single layer is literally all they need to communicate effectively. But what happens when we move them apart?
Well, when distance is introduced, a single layer just doesn't cut it anymore. The tasks have to be divided into 3 distinct layers to manage the new complexity. Notice how at the top level, layer 3, Maria and Anne are still essentially doing the listening and talking part. They're generating the plain text message. But instead of the sound traveling directly through the air, that plain text drops down to layer 2, where an entirely new, distinct task happens, encrypting and decrypting. The plain text becomes ciphertext. Then it drops down again to layer 1, where it's placed into a physical mail envelope to actually be sent and received. Finally, the postal carrier facility physically moves the letter. So you see, the problem of distance is solved by breaking the communication down into highly specialized, layered tasks.
And the ultimate benefit of this modularity is absolutely profound for us as communication engineers. It divides complex operations into smaller, simpler, and much more manageable tasks. But beyond just being manageable, it allows for true independence. Think about it. Imagine Maria and Anne decide they want to completely change their encryption method at layer 2. Because of this modularity, they can swap out layer 2 without having to change layer 3, how they write their plain text, and without changing layer 1, how the post office physically delivers the envelope. It completely separates the services provided to the upper layer from the messy actual implementation details of the layers below it. It's a real game changer.
This brings us to a really critical rule, the concept of identical objects. When we are designing or analyzing networks, we use the idea of logical connections. This lets us think strictly about peer-to-peer layer communication without getting constantly distracted by the physical path the data has to take. So peer layers on different sides are exchanging identical objects. Layer 3 exchanges plaintext. Layer 2 exchanges ciphertext. Layer 1 exchanges mail. Maria's layer 2 encryption process literally only cares about Anne's layer 2 decryption process. They are logically connected, even though the physical reality is that the data travels vertically down Maria's stack, physically across the postal network, and then vertically back up Anne's stack.
Which leads us to Section 2, the TCP/IP protocol suite.
Now let's see how this builds into the real world. We're going to map our human postal metaphor directly onto the digital architecture that actually runs the modern internet. The TCP/IP protocol suite is the foundational architecture. For your studies, and frankly for your future careers, you're going to view this as a 5-layer model. We always count these starting from the bottom up or talk about them from the top down. At the very top, closest to the user, is layer 5, the application layer. Below that is layer 4, transport. Then layer 3, network, which is sometimes called the internet layer. Below that is layer 2, data link. And finally, sitting right at the foundational hardware level is layer 1, the physical layer.
When you compare the modern 5-layer suite to older, original naming conventions, the structure remains incredibly consistent. Just like Maria and Anne's layered postal system, digital communication happens via those horizontal, logical connections between identical peer layers on entirely different machines. Your web browser running at the application layer on your laptop is logically speaking directly to the web server's application layer on the other side of the world. It completely relies on the 4 layers below it to handle all the heavy lifting of actually getting the data across the globe.
Let's look closer at that hardware in Section 3, Network Devices and Duties. With the protocol suite clearly defined, we need to understand exactly which hardware devices operate at which specific layers across the internet. Because here's the secret. Not every piece of equipment on the network uses all 5 layers. If you track communication traveling from a source host, moving through a series of links and devices, all the way to a destination host, you'll see something interesting. The source and destination hosts, your laptops, your smartphones, the massive data center servers, they require all 5 layers to function. However, look at the devices sitting in the middle of the network. A router only requires the bottom 3 layers: network, data link, and physical. And a link layer switch? It operates using just the bottom 2 layers, data link and physical. Why is that? Because a switch only cares about getting data across a single physical link. A router only cares about calculating the IP path to the next network. Neither device cares whatsoever what your actual application message says.
So the crucial point here is understanding the logical domain of duties. The top 3 layers, application, transport, and network, they hold end-to-end responsibility. They establish a logical connection entirely across the internet, from the original source host to the ultimate destination host. But the bottom 2 layers, data link and physical, they only have hop-to-hop responsibility. They are only responsible for getting the data across one specific link. For example, moving data from your laptop to your home Wi-Fi router. Once the data hits that router, that specific hop is finished, and a brand new hop begins.
Okay, a quick tip for your exams in this course. You absolutely must memorize this mapping. Seriously, commit this to memory. Just like Maria and Anne exchanged plain text, ciphertext, and mail, our digital layers exchange very specific data units. The application layer exchanges messages. This is the raw data from your running programs. The transport layer manages flow and error control, exchanging segments or user datagrams. The network layer handles the global routing using datagrams. The data link layer handles single-link transmission using frames. And finally, the physical layer transforms everything into signals, carrying raw bits over the wire or over the airwaves.
Next up is Section 4, Encapsulation and Decapsulation.
We are going to take a journey with a single piece of data to see exactly how it's packaged as it travels down the stack at the source, moves across the physical network, and gets unpackaged as it moves back up the stack at the destination. This entire process is called encapsulation and decapsulation. And what's really fascinating here is that encapsulation is literally just the digital equivalent of putting your written letter into a sequence of increasingly secure routing envelopes. As data moves down the stack, each layer adds its own specific header containing routing and control information. Then when it reaches the destination and moves back up the stack, each layer reads its corresponding header, strips it away, and passes the remaining payload up to the next layer. Let's walk through this step by step.
Starting at the source host, the application layer generates the raw message and passes it down. The transport layer takes that message and slaps on a layer 4 header. This contains things like port addresses to identify the specific application, creating a segment. That segment is passed down to the network layer, which adds a layer 3 header containing the global IP addresses, creating a datagram. Finally, the data link layer receives that datagram and adds both a layer 2 header and a trailer to ensure link reliability, creating a frame. This frame is then converted to raw bits at the physical layer and blasted out over the wire.
Now watch what happens when that data hits a router in the middle of its journey. The router receives the raw bits at the physical layer and passes them up to the data link layer. The data link layer decapsulates the frame, meaning it strips away the layer 2 header and trailer and passes the datagram up to the network layer. The network layer reads the layer 3 IP header just long enough to find the next hop destination. Once it calculates that route, it passes the datagram right back down to the data link layer to be re-encapsulated into a brand new frame, appropriate for whatever the next physical link is, whether that's a fiber optic cable or a copper wire. It's like opening an envelope just to read the zip code and then stuffing it into a brand new envelope.
Finally, the data arrives at the destination host, and the entire process is completely reversed. It is time to open all those envelopes. The data link layer checks the layer 2 header, strips the frame, and passes the datagram up. The network layer checks the layer 3 header, strips the datagram, and passes the segment up. The transport layer checks the layer 4 port header, strips the segment, and passes the pure original message right up to the application layer, into the waiting program. The system works perfectly.
That brings us to Section 5, Network Addressing Basics.
To make sure all those digital envelopes actually find their way through the massive, chaotic global network, we rely on a very strict, multi-layered system of addressing. Just as each layer has its own data unit, every layer has a distinctly different address type that it relies on. At the very top, the application layer uses human-readable names like google.com or your email address. The transport layer uses port numbers, like port 80 for web traffic, to make sure the data goes to the correct running process on your machine. The network layer uses logical IP addresses to route data globally across different networks. And the data link layer? It relies on physical link addresses, commonly known as MAC addresses, to get the frame securely from one physical hardware node to the very next one.
Finally, Section 6, OSI model versus TCP/IP.
To wrap up this explainer and give you the complete academic picture required for a solid engineering foundation, we have to briefly contrast the practical suite we just learned against the theoretical gold standard. The major distinction you need to remember as communication engineers is that the 7-layer OSI model serves purely as a theoretical framework. It's an ISO standard dedicated to international agreement on how networks should operate in a perfect world. However, the 5-layer TCP/IP suite is the highly practical implementation that actually won the protocol wars. It's the one that runs the global internet you're using today.
When you stack them up side by side, the mapping is actually pretty clear. The bottom 4 layers, transport, network, data link, and physical, they align almost perfectly in their purpose between the two models. But notice specifically how the OSI model's top 3 layers, the session, presentation, and application layers, are all cleanly compressed into just one comprehensive application layer in the practical TCP/IP model. The TCP/IP developers found that it was actually way more efficient for application designers to handle session and presentation duties right within the software application itself, rather than forcing the underlying network stack to do it.
So as future communication engineers, you are going to be the ones designing the next generation of networks. And I want to leave you to ponder this. As our physical hardware advances, as quantum communication emerges, and as software complexity grows exponentially, will this 5-layer TCP/IP model eventually be forced to evolve and add new layers, much like the OSI model originally suggested? Or is the principle of modularity we learned today so perfect, so bulletproof, that this 5-layer architecture will act as the permanent standard forever? Keep that in the back of your mind as you head into your next lecture. Thanks for joining this explainer, and keep exploring the stack.